Hello, today I'm taking a look at an example problem to do with single degree of freedom oscillators, free vibration of undamped oscillators. This is just to point out a lot of places where sometimes people plug in the wrong numbers or get the wrong constants out or forget some steps of this. So it's a simple problem as long as you don't make any silly mistakes along the way, and we all do that. That's okay. Let's take a look. So we have a machine that has a mass of 100 kilograms, is currently installed on rigid mounts. The mounts will be replaced by 4 resilient mounts, and each of those has a stiffness of 10 kilonewtons per meter. We want to know a couple things. First is, at rest, how much closer to the ground will the machine be with the resilient mounts compared to the rigid mounts? And then we also want to know what the natural frequency of the system will be after the resilient mounts are installed. So let's just make a little diagram of these things. The first thing, let's look at this kind of before and after situation. So we've got a machine here. Let's just say it has mass M. It's installed on some very rigid mounts. I'll just draw those as like little pipes or something. Then what we're going to do is replace those by springs, resilient mounts. We're going to model as springs. And I suppose I'll draw 4 of them in here. Really, those would be on the corners. But so the first, the part A of the question is saying how much closer to the ground will it be? Well, what I really mean by that is this is going to sag down. It's going to compress these springs. So maybe the mass ends up kind of sagging down like that a little bit. So we want to know what that distance is. And if you were installing these things for real, you would probably account for that and get resilient mounts that are taller than your original. So when it does compress, it compresses, kind of lines it up with where it was before. But let's pretend we're not doing that this time. We're just going to find out what this distance is that it moves down. I'll call that x. So how much the springs compress, we need to just really use Hooke's law. So Hooke's law for springs is the force in a spring is equal to the spring constant times the displacement. Now the tricky thing here is what to use for the spring constant, because I have 4 springs. But what I'm really going to do is model those as one spring, because the forces from the 4 springs just add up. So I'm going to model that as one spring that has a stiffness of 4 times the given value. So we're going to say this is 4 times 10 kilonewtons per meter. The force that we're looking at is just the weight of the machine. So the weight is the mass times acceleration due to gravity. So mass times gravity is k times x, and x is what we're solving for. So x is equal to, let's see, mass times gravity divided by stiffness. And I recommend, when at all possible, just keep doing things in terms of the symbols, and then you can sort of plug in the numbers when you're ready. And now we're ready to plug in the numbers. The mass, remember, was 100 kilograms. So 100 kilograms. Acceleration due to gravity is 9.8 meters per second squared. And then the stiffness, we're going to plug in 4 kilonewtons per meter. We need to make sure we just kind of write that, instead of 40, we need to write 40,000, because we want this in newtons per meter, just to make all the units kind of play nice. So just get rid of all the prefixes except for kilogram. That stays as kilogram. And then you can grab a calculator however you want, but this is 0.0245 meters. And, if you were doing this for a report or something, you probably would write that as 2.5 centimeters. So we got a thing that's 100 kilograms. We're putting it on some mounts. It's going to sag down 2.5 centimeters. And that's that might be pretty accurate for kind of realistic industrial resilient mounts. All right, so then part B, we'll look back up here. What will the natural frequency of the system be after the mounts are installed? So this is just plugging in things. So the natural frequency omega is equal to the square root of k over m. But most of the time we want this in terms of this is angular frequency. Omega is angular frequency. We want this in terms of linear frequency. Those differ by a factor of 2 pi. So 2 pi f is equal to omega. So if you are solving for f, you do 1 over 2 pi, and then this square root of k over m. Again, for k here, we're going to plug in 40,000 because we have 10,000 newtons per meter springs. And the mass is 100 kilograms. And if you work that out, it's about 3.2 hertz. And again, once you do a little, get some practice with this, low frequencies, kind of under, say, 100 hertz, is very, very common for these kind of resilient mounts. And we'll talk about vibration isolation later on. So simple problem. Things that people tend to forget here are the 2 pi. And in general, when something's asking for what's the frequency, you typically don't write that in terms of the angular frequency. You go ahead and go through the effort to get it back to a linear frequency in f instead of an omega. And then the important thing, just in practice, when you're installing resilient mounts, it will make the thing sag down a bit. So you either need to be okay with that, or if you originally need this to be lined up with something, maybe there's another machine that they're connected with a shaft or something like that, you need to account for that and get mounts that are bigger than this height. And then when you install them, they compress, and you kind of do the math to get it back to where it's supposed to be. And that's fairly simple if you just remember this F equals KX relationship. All right, that's all.